In molten salt electrochemistry, the effect of ohmic drop on the scan rate in cyclic voltammetry can be quite significant. It may be tempting to think in molten salts that the resistance is so small that the effect of ohmic drop on the scan rate is insignificant. Typically, we see in molten salts resistances on the order of 0.2 ohms. However, in molten salt electrochemistry, we often use macroelectrodes, meaning the surface area of our electrodes are large enough to have currents on the order of hundreds of milliamps and sometimes over an amp. This high current results in significant ohmic drop effects on our scan rate. On the left here, we have an idealized scan rate portrayed. It's scanning at a negative 100 millivolts per second, and then it switches direction and scans at positive 100 millivolts per second. The result when you run a CV, cyclic voltammetry, is on the right. Here you can see the response at a given applied potential. So the current stays low, and then as we approach negative 1.56 volts, the current rises rapidly, forming a peak and then decaying, and then as we switch, the current begins to rise in the positive direction, and then we strip all of the metal that we deposited off of the electrode, and then it decays back to zero. These sharp rises in currents can create sharp distortions in our scan rate, as shown here with the red curve. This red curve was generated by taking the applied potential and adding our current times our resistance. And so even though we may be applying negative 1.56 volts, it actually may be less due to the ohmic effects. In reality, the electrode itself may be experiencing a potential less than what is applied due to the loss of ohmic resistance. And so this red curve represents what your electrode is actually experiencing if you are not compensating for resistance. And so the scan rate can distort from positive 6 to minus 130 millivolts per second. As well, on the return scan, you can distort from 340 to minus 32 millivolts per second, in this case with the current that's being experienced. These are significant fluctuations that can have a significant impact on your peak current and peak potential, and the shape of your peak as well. And if you're not careful, you may confuse this ohmic resistance effects with quasi-reversibility or irreversibility. Here are some experiment results to illustrate this in practice. On the right, we have a plot where we have a blue curve where we did not apply any active IR compensation during the measurement. And we can see we have a lower peak that shifts a little bit more negative. When we applied 0.1 ohms of compensation, meaning the potentiostat is applying the requested potential plus an additional amount based on the current that's being measured times by 0.1 ohms. And we can see that when we apply that compensation, we get a higher peak and a more sharp peak, and the position has shifted positively. As we continue to increase this resistance here in the plot on the left, it moves from 0.1 to 0.12 to 0.13 to 0.14 ohms. We continue this move to be more positive in potential at the peak and a higher peak current. Eventually, we cannot apply any more resistance, and we can overcompensate, which will result in oscillations and ringing due to the instability in the electronic circuit. So overcompensation needs to be avoided. And so typically, resistance is compensated at 70 to 90% of the measured resistance. And the rest of the uncompensated resistance will need to be accounted for in post-measurement analysis. And to account for distortion, the remaining distortion in the scan rate, simulations must be used.